Galileo Galilei was born in Pisa, Italy on February 15, 1564. He was born the first of 6 children, and although his family wasn't rich, they were considered to be part of the nobility at the time. During his studies, Galileo learned the physics of the ancient Greek scientist Aristotle. However, Galileo questioned the Aristotelian approach to physics. Aristotle believed that heavier objects fall faster through a medium than lighter ones. Galileo eventually disproved this idea by asserting that all objects, regardless of their density, fall at the same rate in a vacuum, known as the law of falling bodies. To determine this, Galileo performed various experiments where he dropped objects from a certain height. In one of his early experiments, he rolled balls down a gently sloped inclined plane and then determined their positions after equal time intervals. One of Galileo's most important contributions to the scientific community is that of the law of falling bodies. This law states that 2 bodies with the same mass and negligible air resistance, if dropped from the same height, will reach the ground at the same time. Using a water clock and an inclined plane, Galileo was able to determine the rate of acceleration due to gravity. With an apparatus like the one in the picture, you could do the same. By timing how long it takes for the ball to roll down the marked distances, you could find out that it takes 1 unit of time for the ball to roll 1 unit of distance, 2 units of time to roll 4 units of distance, 3 units of time to roll 9 units of distance, and 4 to 16, 5 to 25, and so on. Galileo's water clock worked like a stopwatch. To start the watch, he allowed the water to flow into a container. To stop the clock, he stopped the flow of the water. To reset the clock, he emptied the container. By weighing the amounts of water in the container, he could then compare the times it took the ball to travel each distance. For example, if twice as much water, in weight, filled the container, he knew that the time measured was twice as long.
Alright, today we're doing an experiment. We're doing Galileo's old experiment that he did back in the day. Right now we have our water clock in our hand, which we'll be using to measure time, as well as mass. And due to finding the mass of water that we have in the top, after we flip it over, we'll be able to find the amount of time accurately that it takes to roll the plane, which we're doing in our experiment. And that is how Galileo found that gravity is constant and a universal constant all around the Earth. Alright, first we'll be doing the wiffle ball trial, and we'll have 3 trials. Each will be timed from the water clock and an accurate time as well, just to compare. And then after that, we'll average all the times out to get a very accurate time. Alright, what time is it? There. Ready? Trial 2. 3, 2, 1, go. Trial 3. 3, 2, 1, go. Alright, next we'll be doing the tennis ball, which is different radius, so therefore should roll faster down, should take less time to roll faster down the inclined plane than the wiffle ball, the baseball cover. Alright, trial 1, ready? 3, 2, 1, go. 7. Alright, trial 2, 3, 2, 1, go. 6. Last trial, trial 3, 3, 2, 1, go. 6, 5. Now, if we average all this out, this should be greater than this time, due to the radius being smaller on the tennis ball compared to the wiffle ball. And as well as that, we have the ratio of 1 second equals however many kilograms we have from the water bottle due to our indication marks. So let's calculate that now. 89. Tennis ball. Alright, so for trial 1, we have 0.91 seconds, trial 2, 0.83 seconds, trial 3, 0.93 seconds, all for the wiffle ball. That averages out to 0.89 seconds. The tennis ball, trial 1, we have 0.87, trial 2, 0.66 seconds, and trial 3, 0.66 seconds again. And all that averages out to 0.73 seconds. And that is our experiment today. Thank you for coming. See you next time.
For the experiment, we had to take a few pieces of information. First, we calculated that the height of the ramp itself at its highest point is almost a half a meter at 0.46 meters. We then measured the horizontal of the ramp, finding it to be 1.2 meters. Through the Pythagorean theorem, we were able to calculate that the length of the ramp itself was going to be 1.28 meters. Also, the fact that we have to realize that we are starting the ball from rest, there's going to be a no-slip condition, and we're going to be neglecting friction in this experiment. Realizing that we are also talking about Galileo and talking about his law of falling bodies, we're going to prove mathematically why it would be true, using the conservation of energy. So we realize that in this system, there are only conservative forces acting on it, or acting on it with work. Normal force, as you can see in our free body diagram, normal force is perpendicular to the horizontal, to the ramp itself. But the normal force does no work since it is perpendicular. Otherwise, the weight is acting on it. But the weight is the force of gravity. Therefore, it is a conservative force. So the work non-conservative is zero, meaning that the initial energy is equal to the final energy. Once we expand that out, we do initial potential and kinetic energy is equal to final potential and kinetic energy. Now, for expanding that out even further, we have that mg naught plus 1/2 mv squared for translational kinetic energy plus 1/2 I omega squared for rotational kinetic energy. We know that since the ball starts from rest, we know that both of these terms are going to be equal to 0. We know that this first half is equal to mg height final plus 1/2 mv squared, mv final squared plus 1/2 I omega final squared. We also can eliminate this term of the final potential energy since the height will be 0. We then condense that down to mass times gravity times the initial height is equal to the final kinetic energy. As you can see, or what we can do is take this moment of inertia right here. We know that of a hollow sphere, which the tennis ball and wiffle ball are, that a hollow sphere's moment of inertia equation is 2/3 mr squared. We can now sub that into here and get 1/2 times 2/3 mr squared times omega squared, omega final squared. Now, if you look at each of these terms, you can find a recurring mass. Therefore, we can just cancel each one of these out and get the exact same answer. Therefore, making mass irrelevant in such a free falling system. This is just acting in free fall, not in our ramp's equation. And this therefore proves Galileo's law of falling bodies, that mass is it doesn't matter. Now back to our experiment. As you could see before in our free body diagram, which was the first thing we did, we label want F. We have our weight, there's no applied. We have our normal force perpendicular to the horizontal, or perpendicular to our ramp. There's no tension, and we're neglecting friction. So
we can take the weight vector going straight down and break it up into several components. The weight times the cosine of theta, which we have formerly calculated to be this angle of elevation right here to be 21 degrees. So we could have this theta and this theta are similar angles. So we have our weight cosine theta, which evens out with our normal force. And the only force acting in the direction of the ball is our weight sine theta right here. Using Newton's second law, we know that the sum of the forces is equal to the mass times the acceleration. The only force acting in the direction of the ball, however, is the weight times sine theta. So we can plug that in for the sum of the masses, or the sum of the forces. We already know how much our tennis ball weighs, which would be 0.0397 kilograms, or 3.97 grams. And so, or 39.7 grams, I'm sorry. So plugging these numbers in, we have our weight sine theta is equal to our 0.0397 kilograms times our acceleration. We can therefore find out that our acceleration is going to be 3.512 meters per second squared. If we use our kinematic equation, since we do have a constant gravity, which Galileo has informed us of, we can use the first kinematic equation, which would be the final x position is equal to the initial x position plus the initial velocity times time plus the 1/2 of the acceleration times the time squared. Plugging in these numbers, we can find that since we are starting from our origin, the initial x position is 0. Since we are starting from rest, the initial velocity is 0. So we can take both of those terms out of the equation. Therefore, finding that our final x position is equal to 1/2 the acceleration times the time squared. Now, plugging in the information we already know, being the final x position, the length of the ramp, and our acceleration, which we just calculated, we can find that the time that the tennis ball should take to roll down the ramp would be 8.55 seconds. Comparing this with our experimental 0.73 seconds, or 0.855 seconds is the calculated, and our experimental time would be 0.73 seconds. Now, using the percent correct formula that we have here, we can find that we were 85% correct when it comes to the tennis ball, and we have a 15% margin of error in our experiment. Now, moving on to the wiffle ball, we know that it has a different mass, but relatively same radius, which wouldn't matter in this case. We use the exact same formula. The final x position is equal to 1/2 area acceleration times time squared. We plug in the length of the ramp and the mass of the acceleration that we calculated using Newton's second law again, just with a different mass. We plug in our length of the ramp and our acceleration, and we find that the time would be equal to 0.856 seconds, very close to our tennis ball. Finding the ratio between these two times again, and plugging them into the percent correct formula, we have 96% correct and a 4% error on our wiffle ball.
Alright, we have a graph right here which shows the wiffle ball and the tennis ball. We have it with the weight of water over the length of the ramp, and each of these points represents a different percentage of how much water filled up each of the water bottles. And as you can see, the wiffle ball filled up it took a faster time to get down because less water was filled.